So thank you for coming. It's a pleasure to be here. As Lawrence said, we are really sister organizations in the Trieste science system, and I think it's a great idea that we communicate with each other. I think there are fascinating things happening on in different fields, and I think having some communication about it is a great idea. So I'm going to tell you a bit about what I have been doing, and it's actually a very fascinating and exciting topic of research around the world. And I promise not to use too many questions. So I will try to, what I want to convey is the logic of this inquiry, which I think everybody can follow. I'm going to assume that you know a bit about, you remember from your undergraduate days, things like temperature or speed of light or entropy or counting, 1, 2, 3. So that's where Ramanujan comes in, actually. Ramanujan was great at counting, but in a very sophisticated way, I'll explain. So I will try to convey the logic of how research in this kind of a field is carried out, where it's really driven by the essential logic of the subject, because our theories are nowadays are so, we have so much confidence in our theories. When you talk to somebody on the street, when they say theory, they mean like something which is unproven. Theory, like I have a theory that wearing blue makes you feel good or something like that. Whereas I think in mature sciences, theory is really means something, you really accord it a very high status, general theory of relativity or quantum theory, or in biology, theory of evolution. When you say theory of evolution, it's not how normal people understand. They think, oh, it's just a theory, So it's not just a theory. There is a really very deep understanding. And it's because of that, we are able to have the confidence to following the logic of the theory, to say something new, because if sometimes two theories don't fit together. And that's how we make progress, even if you don't have direct experiments sometimes, as I will explain. Okay, so let me now start with very basic thing like time. So you have all heard about relativity, but the fundamental aspect of theory of relativity is the relativity of time. So what do you mean by relativity of time? One of the surprising lessons of the 19th century, 20th century physics was the speed of light is the same if measured on a platform or in a moving train. Now, this is a very weird thing. Suppose you take a tennis ball, which is at rest in a train. Then in a train, the person who's in the train will say that the speed is 0. Whereas the person on the platform will say that, okay, the train is moving at 100 kilometers. The ball is also moving at 100 kilometers. This is not true for light. Person on the train says the light is moving at 300,000 kilometers per second. And the person on the platform doesn't say, therefore, light is moving at 300,000 plus 100 kilometers per second. They all agree, both of them agree that the speed of light is 300,000 kilometers per second. This is totally bizarre. It doesn't make sense if you think about it. But it makes sense if it is possible. If you take this as a fact of nature, then it implies that it must be the case that the way the person on the train is measuring the time is different from the way you are measuring time. And therefore, constancy of the speed of light implies relativity of time. Okay, so this is one slogan you should keep in mind, that if somebody asks you what is relativity, it's a relativity of time. That the time you think that my clock and the clock of the person on the train is the same is not the case. How can that be? Okay, this is I will explain in the next slide. But this, one of the consequences that the speed of light is really like the ultimate speed limit in nature. It's like, you have a sign, 120, 30 kilometers per second. No, you cannot, on a highway in nature, you cannot go faster than the speed of light. From this fact, there are two dramatic implications. One is that there must be gravitational waves, which were detected recently, and there must be black holes. So again, I want to explain to you the logic of it. If you accept that the speed of light is constant in all frames, then time must be relative. Moreover, speed of light has to be the ultimate speed limit, and therefore there must be gravitational waves and there must be black holes. So this logic I want to explain to you first. So relativity of time. So this is a clock. That clock is on the platform and this clock is on the train. The train is moving. Now look what is happening. So when this goes up and down once, you can say 1 second has passed or 1 unit of time has passed. And for the clock that is at rest here, you have to just go this distance, up and down. Let's say half a meter, 1 meter. Whereas if the clock is moving, then it has to actually, if you remember Pythagoras theorem, right? You will actually have to go diagonally. So light has to travel longer distance. But if the speed of light is constant, it will take longer time. Therefore, if speed of light is constant, and if you really think through, so Einstein basically, what his main contribution was to think through, how do I define time? So he said, okay, let me define time by this. I have a clock here, light goes up and down. If it comes back, it's 1 second. But if you accept that, then just from Pythagoras theorem, you can actually derive the light has to run, sorry, time has to run a bit slow for the moving clock. So when you say 5 minutes have passed or 5 units of time has passed, this person would say 4 units of time has passed. And this is the calculation you can do just with high school. I have given it to my son, 13 years old, figure out. And from this, actually, E is equal to mc square follows. So this is, if time is relative, also energy and the relation between energy and mass also changes. So all this amazing consequences of relativity follow from this very fundamental observation that time is relative. Now let me ask you a question. Okay, suppose sun disappeared. When will you come to know about it? So we are going around the sun, right? And you know that it's because of the force of gravity. This much you remember from high school physics, right? The force of gravity is proportional to the mass of the sun, mass of the earth, inverse square law, divided by the distance between the two. Suppose the mass of the sun suddenly goes to 0. You just put 0. Then according to Newton, the force of gravity will go to 0, right? Because force is proportional to mass of sun, mass of earth divided by the distance square. But if there is no mass there, force of gravity has to go to 0. So therefore, what will happen? The earth will just shoot off. It will have no longer be going around. But remember, it takes 8 minutes for light to travel. So this is bizarre. How can it be that gravity, like if I shake my hand here, the mass distribution changes. Does it affect the moon? This question bothered Newton a lot. Newton realized that there was some fundamental problem in his theory. But this action at a distance, where gravity acts instantly, like this, without any delay, sounds totally bizarre, because it means that if the distribution on Earth changes, the moon will immediately come to know about it instantaneously. This is totally, and Newton said that anybody who has a reasonable faculty of mind would not think like this. And he himself though proposed this, the force of gravity. So it was kind of a compromise he did, because he understood that the planetary motions are working well with that law, but there is a fundamental problem. And therefore, if you just remember that the speed of light is the ultimate speed limit, it follows that gravity also cannot travel faster than the speed of light. And therefore, there is a reasonable resolution to it that slowly, when the sun disappears, we will come to know about it. After this thing travels, there is some kind of a ripple will be generated, the gravity wave. And when the wave reaches us, together with light, we'll come to know about it. This looks pretty reasonable. This is called a gravitational wave. This was an immediate consequence of Einstein's general theory of relativity. And Einstein didn't believe in it. And he said that this sounds bizarre. Nobody will be able to detect it. And it took 100 years of experimental work to detect it finally. So since light is the speed limit, force of gravity must also travel at the speed of light. It's a gravity wave. Second consequence is black holes. So I will come to the evidence for these gravity waves and black holes shortly. The second consequence is with black holes. So for example, if I toss this up, that it falls down. If I toss it up faster, with more speed, it will go higher up. If I toss it back even harder, it will go even further. So eventually, if I toss it with a rocket, it will escape the gravitational pull of Earth and it will start. You can put it as this is how we launch satellites, right? Or we launch rockets. So there is something called the escape velocity you remember from high school days. So there is some escape velocity of Earth. If you now double the mass of the Earth, then or increase it by 4 times, the escape velocity increases by 2. This is a square root here, okay? So now imagine you keep increasing the mass of the Earth more and more and more. You will find that or conversely, if you compress the mass of the Earth into smaller radius, then also gravitational force increases. So if you decrease the radius of Earth by a factor of 2, escape velocity will increase by a factor of 2. So if you take the sun has some escape velocity, which is much, much, much larger than the escape velocity of Earth. If you squeeze the sun to the radius of about 3 kilometers, escape velocity becomes equal to the speed of light. And I just now told you, nothing can travel faster than the speed of light. So that means nothing can escape sun. And this is the meaning of a black hole, that eventually, that's called a black hole because even light cannot escape the gravitational pull of that object. And this consequence is so bizarre that Einstein actually wrote a wrong paper, proving because he thought that he had this perfect theory and it's kind of a blemish on his theory, that it is predicting something ridiculous like this. And he actually wrote a wrong paper. It's a very interesting history of black holes, showing why this kind of singularities cannot occur in nature. So this is artist's impression of a black hole. So it looks really black from outside because really nothing is, how do you even see that there is a black hole? Okay, I will come to that in a moment. But there is a more technical definition of a black hole. It's a one-way surface. You can fall inside, but you cannot come out of it. So there's a technical definition, it's called a stationary null surface. Okay, it's stationary, it's sitting over there. It's not moving at the speed of light, but it looks like it is moving at the speed of light. So you cannot, it's a almost self-contradictory thing, but such a thing is possible in the general theory of relativity. But intuitively, it's a surface which is, it's like you can walk into this seminar room, then you cannot leave until you finish the seminar. So, and what will happen to the person who is sitting here? Okay, in my seminar, you will get bored. That can happen. But this person will meet a singularity in their future, where basically the gravitational, that person will be pulled to basically spaghetti. This is the kind of fate you would encounter if you fall inside a black hole. Now, this looks really like science fiction, but Chandrasekhar, a very renowned astrophysicist working at the time in England, proposed that if you take a star which is slightly bigger than the sun, see, why doesn't the sun become a black hole? Because sun has all kinds of huge atomic explosions going on, where there is very hot gas and nuclear fusion is happening there. And therefore, there is very hot gas, which is, the pressure is balancing the force of gravity. But eventually, the sun will run out of the fuel. When it runs out of the fuel, nothing can stop the force of gravity, inexorable force of gravity. So Chandrasekhar predicted that if the solar mass, if it's slightly more than a solar mass, a couple of solar masses, then that star, when it runs out of fuel, will have to form a black hole. And he was so badly criticized by Eddington, some of the leading astronomers of the time, that he left the UK and went to Chicago, partly because he really felt rebuffed by all this. And 100 years later, there is this spectacular, amazing evidence. In 2016, I think he got the Nobel Prize. This is the merger of two black holes, which happened 1 billion years ago. And as I said, the news of that event was a spectacular event. It was so much energy was released. Basically, two black holes merged into a big black hole. And some part of the mass was converted into energy. And that energy was so much that it dominated all the visible energy that was all the stars shining at that time, it was dominated by this gravitational energy, which nobody can see. It's a gravitational ripple, you know. And that ripple then started to travel outwards, and it reached our planet just in 2016. By this time, you know, these descendants of basically monkeys, you know, whose brain had evolved to pick berries and you know, throw stones. We had this LIGO experiment, you know, a 4-kilometer long laser interferometer, just in time. And this wave passed that laser interferometer, and it was detected. And this is a pretty accurate simulation of that event. I mean, using equations of general relativity. This is how, and what is moving around is the space is moving, you know. So all these little dots are stars. So because the space is getting deformed as the two black holes are merging, they go fast, and boom, they will become one big black hole. And then that's the final configuration. And this enormous energy was detected recently. So there is now very strong evidence after 100 years and after many doubters, including Einstein and many serious astronomers and astrophysicists. Finally, after 100 years, the equations somehow are smarter than the people who invented the equations. So relativity describes nature at very long distances, all the way from the solar system to the universe itself, including exotic objects like black holes, pulsars. It generalizes Newton's law of gravitation in the manner I suggested. Newton's law of gravitation was instantaneous, action at a distance, whereas general relativity says that it looks like Newton's law of gravity, but it goes at the speed of light. So it introduces the time into Newton's law of gravity. It predicts gravity waves and black holes. So this is only part of our story. So one part of our story is the description of nature in the 20th century by general theory of relativity, which describes basically everything all the way from the solar system to the universe. Other part is quantum theory. And quantum theory describes nature at very short distances. And this also has been enormously successful in describing atoms, molecules, everything, cells, you know, chemical processes, is basically depends on very peculiar properties of quantum theory. And this underlies much of the modern technology, like this laser that I'm using. And it predicts an antiparticle for every particle. So for example, one of the predictions of quantum theory is that every particle must have an antiparticle. So for example, the antiparticle of an electron is called a positron. Now so these two theories have been enormously successful. I mean, amazingly successful. Actually, if you think about it, you know, as I said, you know, we were monkeys, you know, building some theories. The fact that we are able to understand nature in such perfect detail, in great, you know, we are able to just sit on and calculate on a piece of paper, and actually nature behaves like that, is something which always boggles my mind. And even though the two theories are extremely successful in their respective domain, quantum theory at very short distances and general relativity at very large distances, when you try to bring them together, there is like disaster. And they don't talk to each other. It's like a very violent marriage, you know. So this has been an outstanding problem. How do you make quantum theory live harmoniously with general relativity? And this has been the topic of string theory. So you mentioned that my research is in string theory. String theory is one of the most promising current candidates, which can unify these most important paradigms of modern physics. So, and physics of black holes is kind of, here experimental clues are very scarce. So you have to proceed with just pure thought in some ways, but based on very solidly experimentally verified theories and very solidly understood equations. And I just want to now run you through that kind of that logic about how, just like we starting with constancy of speed of light, I gave you the logic why you must have relativity of time, you must have black holes, you must have. Here, I will tell you, starting with black holes, how do we go to Ramanujan and Hawking? So Hawking discovered that black holes are actually not black. In fact, they are hot. I mean, not in a figurative way. They're hot also in a figurative way because they're quite exciting. But they are actually hot, meaning they are really like a hot piece of metal. They have temperature. And this is known as Hawking temperature. Now, this sounds really bizarre. So again, I want to explain to you the logic. Think about it. A black hole is black. Black means nothing can come out of it. I just told you. But if something is hot, it means it is emitting some radiation. So that means something is coming out of it. So what is going wrong? I mean, just now, 5 minutes ago, I told you nothing can come out of a black hole. And now I'm changing my story. So this story changed with Hawking's amazing discovery. My previous statement was in the context of classical general relativity, without including quantum theory. So that statement is correct. As I said, this is the contradiction between the two theories. You have one theory which works amazingly well, predict black hole, nothing can come out of it. Then you put in quantum theory and there is a violent contradiction. This is a violent contradiction. If you put relativity and quantum theory together, you find that, as I told you, because you have electrons and electrons have an antiparticle, which is a positron. And in fact, even in this room, they are actually, in quantum theory, constantly there is a fluctuation going on. And electrons and positrons are created and annihilated all the time. You don't notice them because it happens extremely fast. So it's well beyond our perception horizon. But they are being produced. Now, if that happens near the horizon of a black hole, then what can happen is that once in a while, the electron can fall inside and the positron escapes. Then the positron has no partner anymore to combine with. So there is a positron sitting outside and it has to go far away. Or sometimes a positron can fall inside and the electron can escape, or a photon and its antiparticle can escape. And it's because of this little fluctuation happening at the horizon of the black hole. Combining, Hawking was able to deduce that it must have temperature. Okay, so black holes are hot, black holes have temperature, and they are like a piece of coal. But that raises another contradiction. Okay. So as I've been telling you, it just goes from contradiction to contradiction. What is the contradiction? And then you try to resolve it and you sort of unify the theory at a higher level. Contradiction is that we have a very good understanding. This is called statistical mechanics. And this was invented by Boltzmann, who, as you know, Boltzmann was a great physicist from Austria. He actually spent his last year and final years in Duino Castle. And he hypothesized that the world is made up of atoms. And in fact, even though the chemists had accepted, going back to Dalton, that the world is made up of atoms, physicists like Ernst Mach, for example, opposed this idea. And Boltzmann actually had some difficulties because of not getting adequate recognition from the physics community, which contributed, he committed suicide. But I'm not saying that he committed it because of this, but it was just to tell you that just 100 years ago, the reality of atoms were not accepted. But Boltzmann explained that, okay, this room is at room temperature, right, at 300 degree Kelvin. Why is the room hot? And we don't see any atoms, right? But we all believe in atoms. How do you know that there are atoms? And Boltzmann said this in 1860, 150 years ago. How do we know that there are atoms? So what Boltzmann did was that he had a kind of a mechanical model of the gas in this room. He said that there are these little atoms of oxygen and nitrogen tossing around. And the number of ways it can toss around. And if the atoms are going very fast, it means you have higher temperature. So he explained the notion of temperature in terms of the energy of how fast the atoms are moving. So now that raises the question, what are the atoms which can explain the temperature of a black hole? Because black hole is a hole in space-time. What are these atoms of space-time? What is the quantum structure of space-time, which will explain why the black hole is hot? That's the question that we are immediately led to. So if you follow Boltzmann's logic, he was able to explain every temperature by mechanics, by the motion of atoms. What is the quantum mechanics of the temperature of a black hole? What is the quantum mechanical explanation of the temperature What are the constituents, if you like, of space-time itself? And this leads ultimately to Ramanujan. Okay, this is the question which is going to lead us to Ramanujan. So, you know about temperature. Now, let me try to remind you of something called entropy. I don't know how many of you remember what it is. Just about it. You have heard about that before, right? So, you know energy. Energy is, so the first law of thermodynamics says that energy is always conserved. This you remember. The second law of thermodynamics says that entropy is always increasing. Okay. Now, I'm going to try to remind you just quickly. Entropy is a very subtle and very profound concept in physics, and goes back to Boltzmann. On his grave, there is this famous Boltzmann equation. So suppose you want to explain the fact that, I can break an egg, but if I run the movie backwards, even a child will say that this is something bizarre. It can break, but it cannot come together. But laws of physics are, if you run a movie backwards for particles moving, it will looks like it is time reversal invariant. So how do we get this lack of, how do we get this irreversibility in our macroscopic world when the fundamental laws are reversible? This is a very deep question. Or why does heat not flow from a cold body to a hot body? Again, it's irreversibility, right? From the point of view of conservation of energy, this is allowed. You can go from hot body to cold body, you can cold body, as long as you conserve energy. So people had tried to devise all this perpetual motion machine, and people said, no, you cannot do this because here energy is not conserved. But here I will give you a process where energy is conserved, but I have to move heat from cold body to hot body, and I cannot do that. So why can I do that? Well, people like Carnot, and they were engineers, they were trying to devise most efficient steam engines, and because of that, this is a very fundamental contribution from an engineer, Carnot. He said that you define entropy as delta Q divided by T. So if you add, suppose you put a heater in this room, okay, you can measure how much heat you're putting in. You look at the electricity bill. Change in the heat that you have put at room temperature, you define this quantity, okay? Change in entropy is equal to the amount of heat you put into this room divided by the temperature, okay? That's just a definition for now. But what Boltzmann was able to, then what Carnot was able to say is that I have a law, the second law of thermodynamics, that entropy can never decrease. It can increase or it can remain constant. And this is some intrinsic property of this. There is entropy of this room, the gas in this room. It's a more abstract concept that you can see. It's not like energy, which you have easy to do. Here I have to do some experiment. Amount of heat I'm adding divided by temperature. That's the change in entropy. Okay, so it's a bit more subtle concept, but it gets even more subtle as I'll explain. But now you can very easily explain the irreversibility. Because why? Suppose when heat flows from a body at temperature T1 to a body at temperature T2, what is the net change in entropy? Well, the body which is gaining will gain. So it is delta Q, this is absolute value of the heat divided 1 upon T2. The body which is losing entropy, you will come with the minus sign, right? The total change in entropy is the entropy gained by the cold body and the entropy lost by the hot body, right? And the lost means there is a minus sign. And if delta S is positive, T1 has to be greater than T2. See, the change in entropy is always increasing. If you believe in the second law of thermodynamics, then you have to believe in irreversibility. But then you might ask, why should I believe in second law of thermodynamics? And this is where Boltzmann comes in. Boltzmann said that entropy is something which is, even though it is macroscopic, you can measure it. You put a heater, at a human length, you put a heater, measure the temperature, you have a thermometer, change in entropy I can calculate. But then he said, it is equal to the logarithm of the number of ways all the atoms in this room can arrange themselves. And this is the most brilliant and beautiful insight of Boltzmann, that with this equation, which is on his grave, he was able to connect something that you can measure in this room. And even though you cannot see the atoms, you can indirectly see the atoms by this relation, because you can calculate this by doing some counting problem. Number of ways, suppose I have n atoms and I have to put them in n boxes. This is some counting problem. This is it's a counting problem. How many ways you can do it? Some factorials and so on, you remember, right? These are counting problems. So if you can do that counting correctly, it should account for the entropy of the room. And what Boltzmann found was that assuming atoms, he was explained to explain the entropy of the gas in this room. So that was his first insight, real direct look into the atomic structure of matter. Even though you cannot see atoms here, you can indirectly predict that it must be made up of atoms if you follow this Boltzmann relation. And Boltzmann relation also explains the second law, because he said that there is a very natural connection. Basically, entropy measures disorder. So suppose you put a partition in this room and all the atoms in this room are on one side. If you remove the partition, what do you think will happen? All the atoms will distribute themselves equally. Now try to do the reverse process. Will that happen? No. Do you think it will happen that all the atoms in this room will suddenly go into one corner of the room? This is very unlikely, right? It looks very counterintuitive. But Boltzmann said it's not so counterintuitive. It's like a jigsaw puzzle. If you shake the jigsaw puzzle, you will not suddenly arrange it. It's much easier with a jigsaw puzzle when you shake it, it will break itself. But just by shaking a broken jigsaw puzzle, you cannot arrange it. So it's natural that just because the disorder, when the atoms are all over the room, the number of ways they can distribute themselves is much larger. And therefore, the entropy is much bigger. And therefore, just statistically speaking, you cannot have the process in which the atoms suddenly go and sit in the corner. Statistically speaking, it could happen in some faraway galaxy that suddenly all of them go and sit in one corner. But if you look at billions and billions of rooms, it is highly unlikely that you will suddenly see this weird process happening. So this way, Boltzmann explained. Now, everything which has temperature has mass or energy must have entropy because of the relation I told you. Because change in heat basically changes the energy of the object. So divided by the temperature. So now Hawking has told you black hole has temperature, black hole has mass. So black hole must have entropy. And that entropy turns out to be proportional to the area of this horizon of the black hole. This black hole that I drew, just look at, it's like a two-dimensional surface. It's a sphere. Its area is like 4 pi times the radius square of that sphere, divided by 4 in some units. That is the entropy of the black hole. And now I come to the final question. How do we explain now? This is the final puzzle. How do we explain the entropy of the black hole in the manner that Boltzmann wanted to explain it? Boltzmann said entropy of anything is related to the number of ways you can arrange that system at the microscopic level. You can have entropy of this room, you can measure it, you can do some experiment, but I can explain it by atomic structure of matter. So now we are asking a question about the atomic structure of space-time. What is that atomic structure? And that takes us to string theory. And this string theory is basically postulates, and it looks like almost a very childish postulation, you might say, that instead of the world being made up of atoms, point particles like electrons and protons, which is what you must have studied in school, it is made up of little vibrating strings. So the electron is actually a vibrating string and a proton is another vibrating string, but vibrating slightly differently. And consistency of the theory with quantum theory requires that you live in either 10 or 26 space-time dimensions, okay? So we live in 3 dimensions and time, so 4 dimensions. Here you need to have additional dimensions. So it all starts to look more and more bizarre, okay? But we are just following again the logic of the theory and the questions that are being posed to us. So what is amazing about string theory is that just like a violin string can have many different notes, it can have do, re, mi, fa. This fundamental string can also have different notes. It's harmonic modes, as it is called mathematically, right? It can oscillate this way, it can oscillate at a higher frequency. And what was quite surprising is that looks like that all the particles that we naturally encounter in our standard model of physics, as it is known in quantum field theory and in gravity, they all can arise from different vibrations of the same string. And this was actually, so this very childish looking idea of having elementary strings instead of elementary point particles suddenly made it possible to think of all interactions, electromagnetic, gravity, nuclear interactions, as coming from oscillations of some one single fundamental string. So this becomes like a unification. This is why it is called unification. And Abdus Salam, the founding director of ICTP, got the Nobel Prize for unifying the electromagnetism with the weak nuclear force. But string theory is even more ambitious. And in a way, we are sort of continuing in that path. This was the dream of Einstein, that we can combine all forces of nature in one single framework and solve all the problems of marrying quantum gravity, marrying general relativity with quantum mechanics. And I cannot explain you why it is so, that will require another course, I would say. But I would like to explain now very quickly. So I have like 10 minutes or so. Where does so string how can string theory be consistent? First of all, you might say 10 dimensions, and we don't live in 10 dimensions, right? So why, it already looks like the theory doesn't make sense. But think about an insect on a wire. Okay? If the insect is much bigger than the diameter of the wire, to that insect, the only dimension that is available is the length of the wire. It cannot really go around and explore the other side of the wire. You need an insect which is smaller than the diameter of the wire to look at the thickness of the wire. So that's how it looks like, that if you can imagine that all these extra dimensions sort of curled up in a little ball at every point. But we are not able to, because they're so small compared to our perception, that we cannot see them. Okay, so this is called compactification. That only 3 dimension and 0 means time. 3 length, breadth, and height, and time. Only these dimensions are accessible to our consciousness and our perception. And the remaining ones are so small, but you can probably see them when you have really high energies. Okay, so it's not like they don't exist. Now, how do you get black holes from string theory? And the question was, how do you understand the gas in this room in terms of motion, right? So Boltzmann said the gas in this room is like motion of atoms. Even though we cannot see them, they are actually tossing around. Atoms are going from there to there, and there are many, many ways you can distribute these atoms. Now, it turns out that a certain class of black holes, I'm going to take a very simple example, that if you look at suppose a string which is wrapping on this internal, it's like a wire, and the string is wrapping the wire. So for us, it looks like it can look like a black hole. For us, it looks like a point particle, even though it is wrapping in some internal dimension. And then in that internal dimension, it could also be oscillating. String could be oscillating in many different ways. And as I told you, so if you have a string wrapping in one direction, and then you take out time, and if I mentioned this number 26, so therefore the number of directions in which the string can oscillate is the number of transverse directions, which is 24. So the string is going like that. There is time. So there are 2 dimensions out of 26 are taken out. And you have 24 transverse directions in which the string can oscillate. So now, this gives you a model of the black hole. And you can say, let's say how many, and actually, you can show that there exists a black hole with the same properties of this string oscillating. So, there is a whole huge amount of mathematics that goes into proving this, which I'm not going to tell you. But the basic intuitive idea is that in one way of looking at it, the black hole looks like a string which is oscillating in 24 dimensions, in transverse directions. Another way of looking at it, it looks like a black hole. And when it looks like a black hole, you can calculate its temperature, as Hawking did. You can calculate its entropy. And you get some number. Now you say that, like Boltzmann, I want to explain that number by looking at how many ways the string is oscillating. And that's where you go to. So you have to calculate how many ways, given some mass of the black hole, which is the total energy of this oscillation, how many ways, I can put the energy in many ways. It can be oscillating in this direction, it can be oscillating in this direction, it can be oscillating slowly with low frequency, or fast with high frequency, and so on. And I need to be able to count that number. And this actually counting problem leads to Ramanujan. So Ramanujan he's considered to be among the all-time greats, in the same category as people like Euler and Gauss, some of the greatest mathematicians. And he really had made profound contributions to number theory. And you must have seen this movie, Man Who Knew Infinity, some of you might have seen. And he was really a person with very singular gifts and very remarkable intuition for numbers. So he could really, as his collaborator Littlewood commented, that every natural number was his personal friend, like that. And he inspired ideas that have kept mathematicians busy for decades. And it so turned out that we were doing this work, and I ended up collaborating with a very well-known number theorist. Some of the problems that we were encountering, I went to ask this mathematician that, okay, have you come across anything? And he said, yeah, but it goes back to Ramanujan, 100 years ago. And it was an unsolved problem, but just 3 years ago, my graduate student solved this problem. And so I can tell you how to deal with it, okay? So, but let me take you the simplest version of it, okay? So I just wanted to take a pause here and tell you. So just the logic, I want to repeat the logic, right? We have seen that black holes exist because of the fact that the speed of light is the upper limit. So something cannot. If black holes exist, then Hawking told you, because of particles and antiparticles, it has temperature. It has temperature, then therefore it must have entropy. Because it has mass, it has temperature, it has entropy. But if it is entropy, then according to Boltzmann, it should be logarithm of some counting, number of ways in which that black hole can exist. Just like entropy of the gas in this room is the number of ways that atoms of the gas can move around. And that counting problem, you can reduce by some work to this very simple counting problem, okay? And so this I want to explain to you. So I give you this following counting problem. You can go home and do this. You'll give it to your child or whoever. Suppose I give you, how many ways can I partition 3? So I can, if I'm just using, let's say just I'm using 2 colors. So I can partition 3 as 1 plus 1 plus 1 all green, or 1 plus 1 plus 1 all red. So there are 2 ways. I can do 1 plus 1 plus red, 1 plus 1 plus red. There are another 2 ways. Then I can do 2 plus 1, 2 plus 1. Then I can do 2 plus 1 this way, 2 that way. So these are maybe, here there are how many? If I did my calculation correctly, it's 10. Now, we will come to this movie where Ramanujan goes to meet McMahon, is a famous, is a combinatorics. This is the problem in combinatorics, right? How many ways you have to count? And this is Hardy, a great number theorist who was the kind of the mentor of Ramanujan, who came from Madras. And McMahon, and you can see there is a very interesting, this was, you should remember, this is pre-war UK. There were all kinds of undertones of racism and so on. So McMahon, you look at the conversation. McMahon doesn't believe that, this guy coming from Chennai or Madras can solve a problem which I have struggled for all my life. So he kind of challenges. Okay, volume. Enter at your own risk.
I've been waiting for you. Square root of 58,639. Now.
242.
242 what?
0.1549090.
Yes, child's play. Try me.
Go on.
Same number squared.
3,438,532,321. Ah! Thrashed ya! Combinatorics, that's what I do. Glorified dice throwing. Bloody nerve of you both. You fail on primes, and you think you can just turn round and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
No, I will. By hand. by slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can do it.
So just to explain to you, he's asking, the problem is, how many ways can you partition the number 200? Just using single color, okay? I give you the number of 24 colors and 2 colors, single color. 1 plus 1 plus 1 plus 1 plus 200 times, or 100 plus 100. No, start writing it, it actually explodes. That number becomes huge, it's exponentially large. So you cannot just do it by hand, you need some tricks. But McMahon, he was major actually, he was a major McMahon, he went to India in some army. So he was Major McMahon, and he was one of the leading experts on combinatorics, and he challenges Ramanujan saying that you cannot do this, you cannot have some simple formula doing this, and you can do it laboriously. I have some tricks and trade for the trade. But Ramanujan had some amazing, beautiful formula, and I won't have time to explain, but he explained that when the number is large, when the P of n, and if you are using 24 colors, has a very simple expression. It's called exponential of 4 pi times square root of n. So look at it. I mean, some strange things are appearing here. Pi is something to do with trigonometry and circle and so on. It has no place, you would think, in counting. But Ramanujan, this is called analytic number theory. We are connecting counting problems with analytic numbers, analytic problems. And there is actually, this is just a simple thing, but here is a simple formula. So Ramanujan just would calculate it like that. Take n to be 200, and this is the leading answer. But he actually has a much more beautiful formula, and that is called the Hardy-Ramanujan-Rademacher formula, which gives you it exactly to exact digits and everything. It's a really wonderful piece of mathematics. And I had to learn it because I was thinking about black holes, and it suddenly came up, that this problem suddenly came up. And so this is the Ramanujan next meeting, he goes back.
Well, here we are, P of 200, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
So now this is my final slide. So as I told you, entropy, here n is the integer, logarithm of the number of ways you can do it. And Ramanujan have told me that it is 4 pi square root of n. And this should equal this area, which you are computing from some totally different. There is gravity, there is space-time, there is no. So, and that goes because of this analytic number theory, as I told you. You are relating some counting problem to pi and exponential, quantities. Pi, wherever pi can come because the area of a sphere is 4 pi r squared, for example, right? So the pi appears in a trigonometric calculation. It will never appear a priori in a number theoretic or arithmetic or counting problem. But because of Ramanujan's relation, when n is large, there is a relation like that. And using that, and this amazingly agrees on the dot. This 4 pi square root of n, we calculate the area. And now this has been repeated in many, many contexts. And I won't go, but I will now quick, I promised you to not show you any slides, sorry, any equations, but this is the one equation I have to show you. So the way he does it is that he defines some function, and if you expand that function as powers of q, then the coefficients give you the quantity that you're interested in. And what he discovered, that this is called the theory of modular forms, that this function is very symmetric. This function has some amazing symmetry called the modular symmetry. So it's a little bit like if I draw some geometric shape, if I have some random shape, if I give you some random function, x squared plus x cubed plus x to the power 4, it has no symmetry. But these modular functions, so it's like drawing some geometric figure which is arbitrary. But these modular forms are like little bit like circles, There are some beautifully symmetrical things. And because they have the symmetry, you're able to deduce their properties in a much nicer way. Just like you can calculate the radius, given the radius of the circle, you can calculate its circumference, 2 pi r. You cannot write down a simple formula like that if you have a Wiggly's sphere, a circle. So using this property, Hardy and Ramanujan were able to do this expansion. And I just want to tell you that this is just one very tantalizing evidence that hopefully we are on the right track. That by computing the entropy of a black hole from two completely different ways, imagining it to be some bunch of oscillating strings, using Ramanujan's formula, and then thinking of it as a hole in space, and this is the signal that we measured, that way of looking at it. The two ways of looking at it, even though they are completely not connected a priori, this formula connects them. In exactly the same way, Boltzmann was able to connect the air in this room to the counting of the number of ways the molecules can move. So in this way, this is we are able to do some quantum theory of space-time, following in the footsteps of a giant like Boltzmann. The way he approached quantum theory of matter, 60 years before quantum mechanics was born, and before you could actually do experiments and you could have electron microscope and you can really see atoms. He did this 60 years before without actually looking, and you don't see atoms, but he was able to deduce atoms. And in this way, string theorists of the day, the 21st century, are trying to learn something about. It's a harder problem because we don't have a lot of experiments as we did in the case of quantum theory of matter. But it is possible to make quite substantial progress using these ideas. I think I will stop here. I just want to say that you have all been to ICTP, and this is, as I said, you must have visited. If you have not done so, please come and visit us. Thank you.